So we're here for the last tutorial I'm going to deliver. I hope you have questions. Maybe we can discuss later. And we should arrange some working groups on several subjects. We have some possibilities, but I hope you are thinking about related problems on your current research that may be addressed and related to these things. So now we're switching to a completely different approach to quantum optimal transport. And the plan is to generalize, or better, find an analog, or better, it will be actually an extension of the optimal transport distance or cost on the discrete Hamming cube. Okay, this will be the Wasserstein distance of order 1 on qubits. We call it this way because it really extends what happens for classical states. This will be related, actually, I told you, when I classified these approaches, I told you it's actually based on the dual. But since I want to be a bit pedantic, I'll start from the primal formulation, although we found it actually in the converse way. First, we thought about a notion of Lipschitz, and then we found the primal formulation. But I think it's maybe usually you present first the primal problem and then the dual. So the dual will be related to a notion of Lipschitz constant, Lipschitz norm of an observable, in this case, which replaces functions, right? Then I show you a couple of applications, okay? The first is an inequality which gives a quantitative continuity, modulus of continuity for the Shannon entropy in terms of this distance. And then the second application is related to concentration inequalities. But there are other applications I'd like to mention. This is quite so I would say a good tool for some applications in computing and information theory. And the credit goes also to Giacomo De Palma, Lloyd, and Milad Marvian, that we introduced first this notion. So let's go back to the classical case that we all love. So what is the discrete cube? The discrete cube is simply the n-dimensional hypercube is simply the set of binary strings of length n, okay? So we already seen this and its quantum counterpart, which is a system of n qubits. Now, on the discrete cube, you can put many distances. If you think of the cube as a subset over n, you may think of the Euclidean distance. But then, if you think in terms of strings, maybe it's more natural just to count. If you have two strings, you just count the number of entries where they differ. I mean, these two are related, of course, because these differences are only 0 or 1, so at the end it's 1 is the square root of the other. So, but taking the square root of a distance gives you a distance, but of course the geometry is very different. So our point of view will be to do optimal transport with respect to the Hamming distance, okay? Now we collect some basic facts on the classical Hamming distance and the Wasserstein distance built on the Hamming distance as a cost, and then I'll try to tell you how to extend it in the quantum case with n qubits. Right, so remember, so our cost is the Hamming distance, so the number of entries where the two strings S and T are differ, okay? So since this is a cost, we can build the usual Kantorovich problem by minimizing over the transport, okay, the couplings would be better, the couplings between the two probability distributions over the strings. Okay, so we are trying to couple the two strings, so transport one distribution of strings into the other by minimizing the number of entries they differ. They're different. Okay. Simple example: if you take a uniform distribution over all the strings, and then you take instead a delta Dirac distribution over a single string with all the zeros, where there's only a trivial coupling, and you get that the cost is n over 2. Okay. Right. So, because there's only one coupling, there's nothing to minimize. Okay. More generally, we're trying to say, okay, typically these two strings differ, or typically on k qubits. We should expect, of course, this distance is between 0 and n, the maximum. So this is somehow in between, right? This uniform distribution is in the center, if you want, of our space. Now, the dual formulation, okay, we know that this is a distance of order 1 because it's built over a true distance on the underlying space. So we know we have a dual formulation. The dual formulation, when you start from a cost which is a distance, is very simple. is simpler than the general formulation. And what you need to know is that you can represent W Wasserstein 1 between sigma and rho as a maximum discrepancy. In the sense you do the integral, this is just the summation over all the strings of f of s, rho of s, so you average f with respect to rho, and you compare, so minus the average of f with respect to sigma. Okay, so you say, and you try to find an f in a suitable class, I tell you which class it is, such that this discrepancy is maximum. Okay, so you're saying, okay, how can I find a good f? Which is our f? Where should our f be? Well, f, we're maximizing over all the f's which are Lipschitz with respect to our cost, with our Hamming distance. So what does it mean? It means that the difference between f of s and f and t will be bounded from above by the number of entries where s and t are different. Okay, just to tell you that this is standard, but specific. So this is a special case. Okay, now some other properties which are more related to the choice of our distance. So for example, if sigma and rho are two distributions over strings, and they have same, okay, now n minus 1 marginals. What do I mean? I mean, think of this as sigma is a probability measure on the strings. So given this probability distribution, you have all the random variables given by the projections. So you can think that you have n random variables, which are simply, if you want, the identity from your probability space into, okay, each of them takes values in, it's just the identity, okay, but you have n random variables, and you say, let's see what happens if I have a distribution sigma here and another distribution rho, such that, for example, if I forget about the first random variable, so the first entry in our string, it happens that the law of all the others are the same. Okay, so the marginal law in the sense that I forget the first one, and I look at the marginal distribution of these other n minus 1 random variables. Okay, now if you forget about one string, remember we need to compare. And it happens that these marginals, for example, the distribution of x2 and xn are the same. Well, you know how to couple now, because what will happen at best, or better at worst? At worst, it will happen that they differ, if you want, in the first string. So the cost, the Hamming distance, should be of order 1, because they may only differ, if you want, in the first. Now, to be precise, what you should do, you should build the coupling in this way. You take the marginal distribution of this n minus 1, which is a probability over the strings with n length n minus 1. You take, which is the same for rho and sigma, and then you take the conditional distribution to define also the law of x1, which may be different in the case of sigma, in the case of rho. Okay. Now, in this way, you build a coupling simply by coupling these conditional distributions, and then you realize that the distance, the cost, is at most 1. Okay. Okay, it's intuitively is natural, but you need to maybe work it out, okay? More generally, if this distribution over strings have the same n minus k marginals, so for example, you say if I look at the x1, x2 up to xn minus k, and I just look at the law of these marginals, of this n minus k, this random variable which takes values into strings of length n minus k, well, if they are the same, then I can do the same trick. So I look at the marginal, I condition with respect to these marginals, and then I just couple what is left. And the cost at most of the coupling of what is left will be of order k. So you can really prove this inequality. Okay. A similar argument is this: if you have a sigma, say is a law of a random variable x, and rho is a law of a random variable q of x, where you have a function on strings which moves only at most k positions, okay? So if you transform your random variables, but modifying, you just, I don't like the first, so I exchange the first from 0 to 1 and so on, but I act only on k positions, well, at most the distance will be k, okay? This is quite natural, okay? So we'll try to see if these properties hold also in the quantum case, Okay, so we will replace transformations with channels and so on. So other properties which are simple but must be checked. Okay, the point is this one. You can always sandwich the Wasserstein 1 with respect to the Hamming distance over strings of length n between the total variation distance and n times the total variation distance. So what is the total variation distance? Maybe, okay, it was in some slides before, okay. But a way to think about this inequality is the fact that the total variation distance is also another Wasserstein distance. Maybe it's not the first definition that you give, but it's just the total the Wasserstein distance with respect to the trivial cost, which is only 0 and 1. So if the strings are the same, 0 cost. If they are different, cost is 1. So with the Hamming, we are being a bit more precise because we count the number of positions where they differ. So you can always sandwich the cost between simply the trivial cost and the n times, because at most there will be n if they differ, right? So if you have this inequality between costs, this will reflect into an inequality between the Wasserstein distances, okay? So, but remember also this, because remember that we have a quantum analog of the total variation, which is called the trace distance. So also this property will hold, okay? Now let's move to our definition on the quantum setting, right? So we want to generalize the notion of quantum or Wasserstein distance with respect to the Hamming cost. But we don't take the route of taking a cost and then taking couplings and so on. And if you want, the good route is to say, okay, I have a dual notion of Lipschitz functions, and I try to generalize that. But let me start instead from another point of view, which may be interesting as well. So the point is the Wasserstein distance of order 1 built from a cost turns out, if you go back to the dual formulation, you see, is a maximum over a set of functions f of a, you see, it's of a linear function with respect to the difference rho and sigma. So actually this is a maximum over a set of linear functions applied to the difference of the two measures. So this is a norm or a semi-norm, okay? So it's a norm. So if you want to describe a norm, you may describe the balls, okay? And so what are the, if you want to describe a ball, you may say, okay, I have a ball of radius 1. How this ball should be done? Well, we start from this observation that if you have two states, so two probability distributions, so that if you marginalize by removing one of these components, the distance was smaller than 1. So what we say this. If you have a system now, our quantum system of n qubits, which is the analog of the cube, right? We have n subsystems, the first, the second, and so on. And what we can do, we can marginalize by removing, so we do the partial trace over the system I. Now remember, we described the partial trace with respect to two systems, but if you have n of them, you just take the partial trace with respect to the ith, and then you leave the rest untouched. So we have operators, or states, over n minus 1 qubits. So for every I, you have a different partial trace. And then you may say, okay, if I have two states, and whenever and actually the point is, it's sufficient to have one site so that if the two marginals are the same, then the distance should be smaller than 1. Okay, because this argument that I told you before to condition and then do the coupling for the conditional distributions, it doesn't really need all the marginals, the n minus k marginal to be equal. It's sufficient only to find one. So this is the same. So we say if there exists a site I, so that if I remove that site, I forget that site, and it happens that the two marginal distributions over the n minus 1 remaining qubits are the same, then I postulate that these are at distance 1. Okay. And now you say, okay, starting from this, I have a notion, if you want, of states that are at distance 1, and then I can, okay, you need a bit to, you want to take the convex envelope, if you want, of these states to do an actual convex, if you want to build a ball. So if you want, the ball is given by the convex envelope of sites. If you want the ball centered at 0, is the convex envelope of sites rho I minus sigma I, right? And I do the convex envelope, so I sum with respect to these weights, which are probabilities, But what I postulate, what I require is that these rho I and sigma I are states that they differ. So if I drop the ith component, they will be the same. So these are states that I postulate to be at distance 1. Okay, so I can build a ball starting from this idea that these these states should be at distance 1. And once you have a ball, you can do the norm by the Minkowski functional. Okay, you just dilate the ball, the first t, so that actually it doesn't even need to be a state x or a difference of states. As soon as x now belongs to the ball, you will declare that it has norm t. Right? You dilate the ball and the smallest t, so that x belongs to t times the ball. Just to be careful, this x. If I just write x, you should always think of x as the difference of two quantum states. Because actually, all these elements here in the ball, you see, these are the difference of two quantum states. So if a quantum state has trace 1, do you remember, right? So if you do this convex combination or any linear combination of difference of quantum states, the trace of this is going to be 0, right? So whenever you see x there, I'm always saying that the trace of x must be 0, right? Otherwise, actually it's the same, right? It's a norm or a semi-norm on difference of probabilities. So you must require to be centered. So the integral of signed measures with the integral 1. Okay. Now, but this is exactly the construction, okay? Starting from this point of view of norms and balls. Now, what happens is that if you now work out all the details, so you have a notion of a ball, you have also this Minkowski functional, you put them together, what happens? If you have two quantum states, the Wasserstein-1 distance between them, so we just write it as a norm so that we remember it's a norm. So it's a norm of sigma minus rho. So what happens is the smallest sum of these weights Ci, where do they appear? Well, I need to represent the difference between sigma and rho as a combination with these weights Ci, which now are not anymore probabilities, right? Because for the ball they were probabilities. Now I just say that this Ci must be non-negative, and they weight this difference of quantum states, sigma I and rho I. And what I require for these quantum states is that if I drop the ith site, they will have the same reduced density operators over the remaining n-1 sites. Okay? Now, this is a definition. You may say, okay, I don't like this definition. I'll try to motivate a different definition based on duality a bit later. But if you want, it's something that mimics a bit what happens in the case of the Wasserstein-1, for example, in the Euclidean case. In the Euclidean case, you can write the Wasserstein-1 of sigma and rho. Now, these are just probability densities, right? You can write it as a minimum over the integral of vector field B, right? Such that the divergence of B is actually a measured valued vector field, gives you the difference of sigma and rho. Okay, so this is, if you want, is Benhamou-Brenier in this, right? This is a total variation. Well, let's write it this way, okay? Integral over all your space RT. Right. So it's a sort of analog of this definition here, okay? You may think of this as a sort of a difference, divergence, of a vector field. I don't see a vector field here, but maybe if you're more familiar with derivations and stuff, you can see something like this. And then you sort of weight, you do the total variation of this vector field. Okay? I think of it in this way, but maybe you see something better.
It can be made formal.
What?
It can be made formal.
Yeah, exactly. It would be nice, because this point of view, okay, we just stick with this definition, we play with it, but it would be nice to really realize, okay, this is really a divergence, and yeah.
It has been made formal, let's put it this way. So it can
okay. Now, okay. Now the important thing is really that we have a definition and we can work with it. I think now the consequence is the important thing, because you can work out a definition or similar definitions. And so the nice thing about this distance, the first thing you realize is that, of course, the order, I mean, these qubits, how do I order them is not relevant, you see, because if you sort of do permutations of the qubits, it will not change, okay? More generally, no, even similarly, but it's a different invariance, is that if you act with a unitary operation only on a single qubit, like you would do in the baby really steps in quantum computing, you need at least then to do more complicated transformation, but if you act only on a single qubit, well, if you act on a single qubit on both states with the same operation, remember the evolution was given by, this is the discrete version of the Schrödinger equation, if you want. You have a unitary, which acts on the left and on the right. And then you can show that this is left unchanged, right? Because if you act on a single qubit, what will happen? That if you have this U here and there, it will enter here. But then if you act on a single qubit, okay, now if well, you really need to write down the U explicitly as acting, say, on the first qubit. So what happens? If you're acting on the first qubit, well, maybe you can see it also from here, okay? If you don't act on qubit I, this will be, the trace will commute with the action of U. If you act on the qubit I, it will enter, and you can use the cyclicity of the trace, okay? This is a bit, okay, half of an argument, okay? Now, but what you can show is that it is not really invariant with respect to any unitary. This is more important, because what we want is a distance which is not unitarily invariant for any U. So for example, if you have a, okay, now maybe we don't have a definition here. You have a controlled X gate, which acts as a basic object in quantum computing that acts on 2 qubits. You can show that this property does not hold in general, okay? So this is a good thing for us, because we want something which is not really unitary invariant for any unitary. We want a different geometry. Yeah.
Sorry. Can I ask a question? I'm not exactly sure what you here denote by sigma I and rho I. Is it like you write sigma as like a sum of pure states?
No. Sigma I and rho I, these are quantum states or over n qubits, okay? Sigma I, even if you see an I above, you need to find this sigma I and rho I with this condition here. Sigma I and rho I must be quantum states. This is because I'm only computing the distance for the difference of 2 states, okay? If you have an X here, if you call X this difference between sigma and rho, you can also find here some Xi's, okay? But you need to find, I mean, in the problem, it's really a problem where you need to find these.
Okay, so we're looking for this sigma.
Yeah, we are looking both for sigma I, rho I, and also Ci, okay? Sigma I and rho I are normalized to be states, and also they have this extra condition that if you discard the qubit I, they will have the same. So now I'll tell you a bit more about what kind of problem.
Just a clarification. So the sigma and rho on the left, they're given, and we are not assuming that they're pure states.
Exactly. No.
So
we're not assuming.
They're just some major.
They're just states.
And here we are looking for those who are pure states, or no?
No. Okay. States as well, right?
Okay.
No.
Still,
they don't need to be pure. No. In general, I mean, if these are okay, these are n.
So it's more like we're looking for certain decomposition of.
Exactly. I mean, if these are 2n times 2n matrices, right? Sigma, and if they're not pure, you may think they have full rank, right? At this point, if we require sigma I to be pure and rho I to be pure, at most the rank on this side will be 2 times n, not 2n. So it would be very strange to require all sigma I and rho I to be pure for a general case. Now, let's move to other simple properties that we can prove. You need to work out with the definition. Would be a good exercise also to work them out from the dual definition that we're going to see in a moment. So I just list them as properties. Okay, so if you have products states in the sense that you have a state rho, state sigma, sorry, on m qubits, and another same joint state here on the another n qubits, you can take the product sigma tensor product tau, rho tensor product tau. This will be states on m plus n, but they share, if you want, this tau. And of course, probabilistically, you will say that this gives you independence. So what you can prove is that if you want, you can couple this tau so that the cost is 0, and then you will have only the cost between sigma and rho. Okay, you can prove it starting from the definition, but it makes sense. Now it's more intricate, this thing, because somehow it can be tricky. You have a super additivity, let's call it this way, no? So if you have states rho and sigma over n plus n qubits, and you look at the marginals, so the reduced density operators, so you trace out, here I trace out the remaining n plus 1, n plus n qubits. And here I trace out the remaining, why there is n here? I should do the same thing for rho, okay, rho 1, rho m. So I look at the marginals probabilistically over the first m qubits, and then the marginals over the remaining n qubits. But you can show that the total cost is at least the sum of the two costs. Okay. One should be not confused. I saw some papers in classical case where they argued that the other inequality is true. No. Okay, this is the correct inequality. And then you can prove that the equality holds if they are products. Okay. Well, these are simple properties. An important property as well that holds is that, again, we have a trace distance between, okay, the trace distance is 1/2 the trace of the absolute value in the sense of matrix calculus of sigma minus rho, okay, of operator calculus. This is a trace distance, and it's, again, sandwiching up to a factor n, the Wasserstein distance of order 1. And similar, you can show, but this is more or less a circular argument, that if you have two states, so that if you trace out one qubit, say at site I, and the remaining, the reduced density operators are equal, then the distance, well, and okay, this is slightly more informative, right? Because you know that this trace distance will be always between 0 and 1. It turns out that the trace distance equals the Wasserstein distance of order 1, if you have this property. If you have this property here, we have postulated that the distance between rho and sigma will be smaller than 1. You can actually say that it will be equal to the trace distance, okay? Which is, if you want, is a more precise information than what we started with, okay? Now, okay, these properties may be also shared by other kinds of distances. Not all the distances, however, one can think of recover the classical distance over the classical states. Because remember, if you have a state which is diagonal on the computational basis, so if you remember, you have this basis given by the products, the pure states, which are indexed by these elementary tensor product states over the sequences. If it is diagonal, the matrix operator is identified with a classical probability distribution, right? So what happens is that the quantum distance of order 1 between the two quantum states actually equals the classical Wasserstein distance with respect just to these classical probability distributions, okay? Now, I don't know, maybe, okay, let me say, this is not the only distance which satisfies this extension property. For example, there was an approach by Agredo which can extend any distance given on a basis. So I guess in this case, I think also his distance shares this property, okay? But this comes up to be, I say, more natural. You will see also the duality. Now, how do you prove this statement? Remember, you have first of all, if you look just at the classical states, for example, diagonal states, which are discrete Dirac distributions, so just pure states indexed by one sequence X and another sequence Y, these are product states. So if you use this tensorization property, where you have equality because these are just pure states, but will be just the sum of the distances between the one marginals. But then the one marginals is really, these are orthogonal states, and the trace distance is 0 or 1, according whether the components of the sequences are equal or different. So for these very simple states, we have equality, at least. And then you say, now, if I have a classical transport plan, I just use this transport plan to build a coupling, so sort of a coupling, okay, no, not building a coupling because this is not our definition, but I plug it here so that I can represent rho minus sigma as this sum here. Sort of, this is already an identity. And then you use the fact that the Wasserstein distance is a norm, so I just use the triangle inequality, and you end up with this. Okay, so the Wasserstein distance is always cheaper than the classical distance. But this was also a fact that was true for the other distances I told you, right? If you move to the quantum case, you have more dimensions where you can work with, so you expect things to be cheaper. So the point is to show that these are really equal. And how do you prove that these are equal? So you start with a decomposition, as I told you, right? You need to search any decomposition, right? Sigma minus rho, you write it as a sum of Ci and difference of states sigma I and rho I, where these are quantum states, such that if you do the partial trace, you trace out the system I, they will then become equal. Okay. Now remember, if you have these are classical, right? Sigma and rho. Classical in the sense that these are diagonal matrices. Here, these are not required to be diagonal. But what you can do, you can always say, well, let me put all the components that I have of the diagonals for sigma I and rho I put them to 0. Okay? So if you do this, you know that the identity will hold anyway because this on the diagonal is already 0. So, but remember, if you just take your matrix operator and you look at the diagonal, you have classical probabilities. So you end up with looking at just what you have on the diagonals here, you end up with classical probabilities which represent the classical the difference between the two diagonals as the sum of differences. Okay. Now what happens? The condition that the trace, if you discard the qubit I here and there, they will give you the same marginal, means really that if you discard the bit I marginal from Pi and Qi, they will be the same. So what happens is that these two are at classical distance smaller than 1. Okay? And now you have, for example, that the Wasserstein one, also in the classical case, is a norm, so you use the triangle inequality and you end up with that. Okay? So this is a difference with respect to the distance built with the channels and stuff. So it happens that on these classical states, you are not improving. You are extending instead the classical distance, which is maybe a good property. Another important thing is, some remarks before we move to duality, okay? So we have this sort of Monge problem, but we don't have transport plans here. But of course, if you look at this problem, you say, how can I actually compute numerically these things? So these are states, general states. So, okay, you may say this is a positive semi-definite problem because there is hidden here a condition. So you have this linear constraint. This is another linear constraint. Ci must be non-negative. You are minimizing. But you also have the condition that rho I and sigma I are quantum states, so they have trace 1, but also they're positive semi-definite. So this is a positive semi-definite problem. And the dimension is huge, I would say, right? Because you have, these are 2 to the n matrices, right? So 2 to the n times 2 to the n matrices. Would be nice, I don't know, if you are expert in this subject, to see if it's really out of range. As far as I know, the best that people tried was to do n equal, I don't know, maybe 5 or 6, I don't know, but maybe because it's, okay, so it's interesting, and maybe there are some smart ways to do something here, okay? Because it's usually, so it looks like a good candidate for a good distance. It would be nice also to have a good way to compute or approximate it. Notice that we have seen a lot of these entropic regularizations, but if you don't have the plans, the couplings, I don't see a way to put immediately an entropy here, right? Maybe you need to work a bit in a different way. So it would be interesting to understand this.
Now,
yeah.
Do we have a formal proof of that the computational cost grows exponentially?
No, I don't. But I don't know. In fact, maybe it's. I will say you just you know that if you have exponential with n, you know that these are matrices that are 2 to the n. Well, already storing the matrices is exponential in n. So I guess the algorithm would be.
I mean, everybody believes this is hard to calculate
right.
the distance, but I mean, there's this other statement. Can we actually?
Well, okay, you may say already storing the matrices, but for example, it might be, but depends if you're there are some, these exponential improvements in linear algebra, if these HHL theorems, and you say, okay, maybe I have already stored my quantum states in the quantum computer, so I don't care about this part, so let's see only the computational part. There may be a lot of possibilities here. I would say maybe classically is more interesting to.
So let's say that you found the optimizer for this Munch problem.
Yeah.
Does this tell you how to, I don't know, make a circuit or something like this that will transform one state to the other, or?
No, because you say that would be related to a channel or a coupling. Well, a circuit is already a unitary, and that would be too much, right?
Maybe set of slopes that you see that it's not like you were like some kind of slopes or I don't know what. Well, it's kind of a coupling of the classical thing, which is the CI, which you could dilate.
I mean, from this primal formulation, as far as I know, they don't. I mean, if you look at the dual formulation, you can think maybe a way to approximate it. From the primal, I'm not very aware of this, because you don't really have these plans or couplings around.
So the divergence is not really.
I mean, so I don't know. Maybe so far nobody has seen.
One thing is clear: if you want to test this with linear tests, right?
Sorry?
If you test with linear tests, then you're simply testing against the Lipschitz functions. Some entropy.
Yes, but we are more on the duality. Yes, now I tell you a bit more about the duality. Maybe the duality suggests, but it would be nice to have something directly on the primal. As you do in the classical transport, you add the entropy, you say, yeah, I'm fine with that, and I look at Sinkhorn as Augusto explained. In this case, I don't see it. So other generalizations, and so far we discussed with qubits. So it's possible to possibly one can generalize. I don't know if people has already done it or not. To move to qubits, you can do it, and then you maybe do directly infinite-dimensional systems on each of the factors. Another more interesting limit that we did is to do the limit of infinitely many spins. Okay, you do this. Of course, this distance will grow as n grows, so you need to renormalize and divide by n. You have a sort of this density, relative distance, so specific distance. Okay, but there are many other generalizations. For example, what happens if in one of these factors I have another notion, instead of just saying that two distances are distance one, for example, you have other geometries on a specific factor, you may try to take this into account. Now, what we're going to do in the rest of the talk is to look for a dual formulation and see if we find out a dual formulation which exists. We know because this is we recognize is a convex optimization problem, so it must have a dual. Actually, this is a norm, so there will be a notional dual norm. And the dual norm, we realize this Wasserstein distance in terms of a maximum over what? Over observables, which are the natural dual space, as the trace of h times rho minus sigma, which mimics what happens in the classical case. You have the expectation of IH with respect to rho minus the expectation of h when the state is sigma. And then we're going to have this notion of dual norm, this Lipschitz constant of h. So how is this defined? Let's go back to the classical case. In the classical case, the Lipschitz constant with respect to the Hamming norm is just a Lipschitz constant, but when here the distance is computed in terms of the Hamming distance. So this is actually equivalent to require that the function has so-called bounded differences. So if you have two strings which differ in k positions, their difference of f will be smaller than this constant times k. In particular, if k equals 1 is enough, actually. Okay, so this is an exercise if you've never seen it. So we want to mimic this thing. So what does it mean that the two strings differ in one positions? We already know. And in fact, you can say, well, we can define the norm, the Lipschitz norm, as the dual to Wasserstein 1. Okay, this is just a definition which self-referring. We want to have instead, okay, we can define this object in this way, but now, of course, you can recover the first norm. We are in finite dimension. Everything is no problems with everything here, with spaces and so on. You can recover also the Wasserstein distance with duality, but this is just, say, abstract things that work anyway. So what we want, which is interesting, is that you can find this sort of more natural definition, operational definition of the Lipschitz norm. So the Lipschitz norm of an observable will be 2 times, okay, you do the maximum over the sites, so you have maximum over the first, second, and nth qubit of what? Well, you try to say how much h changes if I compare it with an observable which do not depend on the ith coordinate. How do I say it? I just take the identity over the ith system and I do the tensor product with another h, any other observable h, which instead is unobservable on the remaining n-1 qubits. Okay? You need to think of this as a function which depends on all the strings, on all the sides of the string, and this is a function which does not depend on the site I. Okay? You try to do how much is the difference. How do you compute this norm? This is just the operator norm. Okay? And this is a better definition because you may think, okay, now I can relax this notion here. If I relax this notion, maybe I will have an approximation of my Wasserstein. Using the duality, I will have an approximation of my Wasserstein 1. Okay, maybe I can skip. I mean, you have to understand, you have to prove that this is the correct definition, because if this is defined in abstract terms, you need to check that everything works out. Okay, maybe I skip this part, but it works. Yeah, let's skip otherwise. So what happens? Given that definition, you are doing a sort of oscillation, so bounded differences, you fix any site and so on. But for example, for sure, you can always try to compare h with respect to a function which does not depend on any coordinate, which means the identity operator in the quantum setting. So the Lipschitz semi-norm is always smaller than 2 times the minimum. If you want, this is a sort of oscillation of h. What does it mean in terms of spectrum? It means exactly the maximum eigenvalue minus the minimum eigenvalue. Okay, this is just, I guess, no, divided by 2, right? So maybe here there is something. But anyway, you can always bound this with twice. Yeah, maybe this is very, very. Okay, up to a constant, which is 2, you can bound it with the operator norm of h. Okay, so you can always bound. So it's a smaller norm, the Lipschitz constant. How should you think of this? Well, a function, classically a function can have bounded difference of order 1, but of course, if the space in the classical case has diameter n, so you would expect that this can be of order 1 and this should be of order n. Okay, so of course, they should be one smaller than the other. Now, it's more interesting instead to notice that if you have an observable which is a sum of local operators, so sum of observables that only act on qubits on a subset of all the qubits, you can be more specific using precisely this decomposition. You can show that the Lipschitz norm is more than twice the maximum of the sum of these local operators, and you do the operator norm, but you restrict the sum only on the sites on the subsets I, which contain small I, the site that you choose. What do I mean? I mean, this sum could be a sum of a lot of these local operators, but if I fix a single site, perhaps the interaction is only between one site and the next one. So even if I had, say, order n of this, if they're arranged like this, these qubits, if I have site I, perhaps I only have interactions between the site and its neighbor, so perhaps this sum is much smaller than just doing the summation over all. Okay, and this is a good property of this Lipschitz constant. Okay, some exercises, but let's skip. Okay, maybe we can move to some applications. Okay, because we can work out many definitions. Let's see if this is a good definition in sense of applications, at least in theory. I'm not saying that it's good for computational point of view for the moment. So, so just to recall you that the Shannon entropy was defined as minus the sum of px log px for a probability distribution here over strings in this case. And instead, the von Neumann entropy is minus trace of rho log rho for a quantum state. Okay, now one can ask, is the entropy a continuous quantity? So if I change a bit a probability distribution, remember, the entropy is the number of bits that you need to describe, to code, if you want, a source of messages which are IID with this probability, marginal probability, right? So the number of questions with binary answers that you need to ask to, say, codify to your message. Okay, so if I change a bit this distribution, will the entropy change a bit, not too much? So is the entropy continuous with respect to some metric? So apparently this question was not very much studied already in the classical case. And Polyansky and Wu some years ago, but perhaps there are also other results. I don't believe that this is the first, but this is the first result that we were able to show, to find on the cube. Well, they show explicitly that the difference, the absolute value of the Shannon entropy between two classical strings, probability distributions over strings, is bounded from above by n times, this is the binary entropy function, and then inside as an argument you have the Wasserstein distance of order 1 with respect to the Hamming metric divided by n, because this is of order n, you should think, so you divide by n, so this is between 0 and 1. Now this H2 is the entropy of a Bernoulli distribution, okay? Now what does it mean? This quantitative result, what does it say? For example, if you have a source which is uniform, which is uniformly distributed over all the strings, and you have y, which is another source which is close to x in the sense of Wasserstein distance. So very close, say much smaller, the distance is much smaller than n. So you're very in a small neighborhood, if you want, of the initial source. Well, then also, since the entropy of x being uniform will be of order log of 2 to the n, because remember the number of elements is 2 to the n, so the source will have entropy n, but also y, given this inequality, will be of order n. Okay, this is what happens if, of course, if you have this requirement that this is very small, because this binary entropy will be essentially very small, it goes to 0. Okay, so this is a good thing. Let's see if in the quantum case something similar is known. Well, for states over a system with dimension d, there is this inequality by Fan and Audenart that slightly improved the inequality. Essentially, you can prove that the von Neumann entropy is as modulus of continuity, if you want, bounded by this quantity here, where on the right-hand side, you see you have 1/2 the L1, so this is the trace distance. This is what the factor 1/2 is because of normalization, okay? So you have the trace distance. The trace distance and the binary entropy function, so you say, well, this is very good. But also here you have an extra term, which is logarithm of d minus 1. And now remember, if d is the dimension, we should plug for n qubits, d equals 2 to the n. So this is a term which grows like n, which is okay. I would say because also the entropy should grow like n. Now what happens? For n equal 1, well, for n equal 1, the trace distance actually equals the Wasserstein distance of order 1. So this is really Polyansky-Wu. Now, what happens instead if n becomes very large? Well, here on the right-hand side, we have the trace distance, while Polyansky-Wu has the Wasserstein distance divided by n, of course. Now, what happens? It happens that if n grows, let me see. I'm saying that this is useful only when this quantity, yes, the trace distance is smaller than 1. What is the problem? The problem is that if you have two states which may be very close from a Wasserstein distance point of view, they may be very far from the trace distance, right? For example, if you take a site which is probability pure state over the distribution with all zeros, and you take another distribution which is one component is 0 and all the other ones are 0, right? So from the point of view of trace distance, they will be extremely far, right? Because these are orthogonal, so the trace distance is of order 1. But from the point of view of the Wasserstein distance, this is also of order 1, but we expect to find the Wasserstein distance divided by n. So if you normalize with taking into account the number of sites, they should be much better, right? So essentially, we want to find roughly an analog of the Poliansky V for the quantum case. And this is something you can work out. And actually, it looks very, very similar. The only difference, if you want, is this extra factor here, which is, okay, for qubits is 3, otherwise it's d to the squared minus 1, if you have a system which is of dimension d, and you take a product of d of them, okay? So let me say, this kind of questions on the continuity of the Wasserstein distance, they're not very much explored, but there are, for example, they might be interesting to find some free analogs of these inequalities. There are also some inequalities in the continuous case. Poliansky and Wu also proved similar inequalities, quantitative moduli of continuity for the Shannon differential entropy, okay? So you need to assume some conditions on the distributions. So it would be nice to explore a bit more this kind of inequalities, okay? Well, another important,
yeah. Is there any hope that you remove the second plus term? Is that possible, or is it? I mean, is it conceivable that the second plus term does not even have to be here?
This one, the log. Yeah. No, as far as I remember, but it's been a while. We were convinced that this is actually it's sharp with log n d squared minus 1. So
you need the second term.
Yeah. I think if you want a simple question would be if I just assume here for the finite Sautenauer.
This one is definitely sharp, but the question is, in the Poliansky Wu, you didn't have a second term, right?
Well, but for them there is d minus 1 instead of d squared minus 1, so it's
there's no plus term, right?
Yeah, but it's hidden because it's on binary strings. If you are on non-binary, so if you have on d strings, it's a logarithm of d minus 1. So you are, it's there as well. Okay, yes. Yeah, but for sure you can ask in other settings. I don't know how much this question is asked if you have explicit continuity. And of course, you can also divide everything by n, which is the right scaling. And if you let n to infinity, you can prove also something which holds in the limit for the specific, as I told you, this notion of specific Wasserstein distance for infinite dimensional systems in the sense of infinitely many sites. Okay, let me show a final application of this kind of ideas. So it is known since as I told you, right, the Lipschitz constant is bounded from above by twice, maybe, I don't know if it's correct, twice the L infinity norm. And of course, you can show also that the system, so if you take the set of the system of n qubits, it will have a diameter which is smaller than n. You can show essentially that if you have a Lipschitz observable, all the eigenvalues will belong to an interval of size n, okay? If you want, it's like having a function with bounded difference. If the differences are bounded by 1, the diameter is n, I can see at most a range of values which is of order n, okay? Now, what happens instead, this is quite interesting, is that you can show that most eigenvalues actually belong to a much smaller interval. You have so-called concentration, and the size of the interval will be of order square root of n, the Lipschitz constant. Okay, this is a fact that is also known in the classical setting. These are based on concentration inequalities. So in the quantum setting, how do they look like, these concentration inequalities? Well, you need to be careful because you're not counting the eigenvalues, or better, you're counting the eigenvalues with multiplicity. So what you do is that you take a small delta, positive, and you look at the dimension of the space of the, if you want, of the space generated by the eigenspaces where the eigenvalues are larger than okay, you just need to, let's say, for example, that the trace is 0, so this looks much simpler. So assume that your observable is 0 in average. Okay, so forget about this. You look at the dimension of the eigenspaces generated by the eigenvalues which are larger than delta square root of n Lipschitz norm of h divided by 2. Okay, well, you can show that this dimension, if delta is large, will be exponentially small. Okay, typically the total dimension of the space is 2 to the n. So if you divide by 2 to the n, you have a sort of probability, and this will be very small, exponentially small, with exponential to the minus delta squared. So this is a sort of Gaussian tail behavior of this.
Here the assumption is that h is kind of a Lipschitz.
Exactly. But you see, you have the Lipschitz. I mean, everything is Lipschitz here because we're in finite dimensions. So a Lipschitz constant, you will have some. But of course, it's interesting because you have the Lipschitz constant here, not the uniform norm. Okay. So you have this Lipschitz constant, and you can get this concentration inequality. Now, how does it work? So if you want roughly, if you think in terms of probabilities, you may say really. I have a sort of a Gaussian tail behavior, so the eigenvalues are distributed like a Gaussian, so no, not really something very precise, but roughly like with Gaussian tails, like a Gaussian with mean trace of h divided by 2 to the n, okay? So this could be 0 if you center h, and the standard deviation is over the square root of n, if I did the computation right, square root of n Lipschitz norm of h divided by 2, okay? So the important thing is you have this square root of n and not n. Okay. So how does it work? Well, this is a general strategy that works in the classical setting. So you may think I can prove directly this kind of inequalities. Maybe not directly these, but for example, I can move classical improbability. You will move to moment generating functions, and then you apply Markov inequality. Or Chernoff bounds. Otherwise, you can argue by duality. Instead of looking at functions, you look at probabilities. And so you try to establish an inequality of this kind. These are so-called transport entropy inequality or Talleyrand inequality. There are many inequalities by Talleyrand. So essentially, we need an inequality of this kind, classically, where we bound the Wasserstein distance of order 1 between two probabilities with respect to the square root of, inside you have the relative entropy of the Kullback-Leibler divergence between P and Q, and you have a factor n because of scaling, okay? You must have something like that goes like n in our setting. And remember, this is Kullback-Leibler. So essentially what happens, if you can establish this inequality for a given Q, so Q is what happens here, because this is not symmetric, okay? We have the one we have on the right. If you want the prior, like Tryphon was saying, right? If you think of this as a prior, if you can prove this for any P, given a fixed Q, then you can dualize everything, and you will get a form of Gaussian concentration. Now, what kind of Qs can we expect here? Well, you can prove, Marton, I think she was one of the first studying this kind of inequalities. You can prove, for example, where Q is a product state, also in our case will be a product of states on a single qubit, or there are a Q which is, for example, a state Markov state, so the law of a Markov chain, under some assumptions. So what we do, we establish this one for product states. The issue, if you want, is when you dualize. In the quantum case, we have some trouble. We don't end up directly with this. We end up...
Product state Q is a product state?
Yes, Q. The reference, the prior will be a product state, okay? So if actually you can think really of a product state of the identity. So you just take the identity divided by 2 to the n. This is already enough to get this inequality here, okay? The point is that you can prove it also for a product states. There's been some development by Cambise and De Palma. They moved to Markov, sort of Markov states. It becomes more technical, but it's interesting. What I find still interesting is that essentially the moving from this to the dual looks not completely immediate or showing the equivalence. In fact, Marius told me they have a sort of a complete argument. This would be interesting to understand, for me at least. So how do you work this proof out in the case of a product state in a quantum setting, okay? So in the quantum setting, essentially you look at the paper of Marton, you say, maybe my definition works exactly as in her proof, but actually no, it's not immediately that one, because we have a slightly different proof. If you want, the original proof works by conditioning, because in the classical setting, you can work always with conditional probabilities, while in the quantum you don't have. So let's say that our Q now becomes sigma and is a product state, and we want to prove this quantum Martins inequality, okay? Or if you want Talagrand inequality on the product state. And now the relative entropy is the quantum relative entropy, okay? Now, how does it work? Well, first you check, at least if for n equal 1, it holds. And actually for n equal 1, it was known, because for n equal 1, since the Wasserstein 1 is sandwiched between trace distance and n times the trace distance, it's really the trace distance. So for the trace distance, it is known that you can bound always, for any sigma, you can bound from above the trace distance by square root of 2 times the relative entropy. This is known as Pinsker's inequality in the quantum setting, quantum Pinsker's inequality. Now, maybe I skip the proof, but I just leave for completeness. It's quite nice, the proof, because it's not really not really immediate, as you would do in a classical case, maybe. Now, what happens then in the quantum Martin inequality is that we have the case n equals 1, and we want to argue by induction over n, since it's a product. So remember, in our definition of Wasserstein distance of order 1, we need to find the composition of rho minus sigma as a sum of this rho I and sigma minus sigma I with the weights ci. Okay, so what we do like this. We write rho minus sigma as this sum here. This is a sort of telescopic summation. Okay, rho 1 up to I is the reduced density matrix over the first I qubits, and then sigma I plus 1 n is the one over the remaining n. So you have this telescopic summation. Now, what can we say about this? Well, we can say that at least the total variation distance, well, maybe there is a factor, sorry, the trace distance up to a factor 2 is bounded using Pinsker's inequality. Pinsker's inequality tells you that the distance, the total variation, the trace distance, sorry, between this difference is bounded by a square root of 2, the relative entropy. Okay. Now, the relative entropy in this case is good for us, because we're going to see a bit in a second. Okay, now, if you sum over I this quantity, you will have a sum of square root of relative entropies, and now you use the fact that the square root is a concave function. Okay, so you take the square root out, essentially, up to a factor n. So the only thing I'm just going to say, yeah. Okay, now you can show that this sum, right? Yeah, these are okay. You have to be a bit more careful. Now the sum. This is not. You see, you don't see maybe these CIs here. Okay, but okay. Given a representation of this kind, if you do the sum of the total variation distances of these elements you have here, you can bound from above the Wasserstein distance of order 1. Because what is the point that these two, call this rho I and this sigma I, you see, they're different. If you trace out the state, the site I, they will have the same marginals. Okay, so these are really candidates for our representation. The only point is maybe here you don't see the CIs, but because they are somehow hidden a bit in this representation. Okay, and so okay, we have a good inequality. The only point is that here we have just this summation of these relative entropies that looks a bit nasty. But the point is now you recall that the sigmas are all products. So far we didn't use anything about the fact that one or the other were products. Okay, this holds in general actually. Now the only part where you use that these are products is that when you look at these relative entropies, you have a product here. So you see all of these factors, so from I plus 1 to n, also here you have sigma I tensor sigma I plus 1 and so on, all these other factors cancel and you end up only with this one. Okay, here you use the fact that this is product. And finally, you just need to work out the definition of this relative entropy. You have this identity and things will So you have a telescopic summation, this will work out fine. Okay, so we only use the fact that this is product here. So far, it's a general inequality. I don't know if it can be of any use in this form, but...
This formula is called chain rule.
Yeah, no, I mean, this chain rule, yes. But this instead is a telescopic summation where you apply the chain rule. I mean, yeah. Now, okay, if you go back to Marton's original proof, it's again based on, is by induction, if you want, by this tensorization and stuff. So the only thing is if you want, it's overly complicated, because if you have this, you can also use this definition in the classical case. It gives you a proof without using couplings of the proof, which is interesting, maybe. Okay, and once we have this, no, maybe we just skip. I'll just tell you that, oh no, maybe this is good to show, because we have also Marius which can comment on this. So the point, okay, let's say that we have proved, oh, maybe you don't like the proof and so on, but let's say that we have our Marton or transport entropy inequality. How do we move from that to concentration? This is interesting as well, because it's a more general effect than the thing we showed before. So assume, just for simplicity, that our H has trace 0, so just add a multiple of the identity, and the Lipschitz norm is equal to 1 or smaller than 1. So what you just need to prove is that the trace of the exponential of TH is bounded from above by 2 to the n, which is the dimension of your space, and then this exponential of n t squared over 8. Now, the important thing is that you have a t squared here and a t here, which is, if you want, the thing that you would have for a moment generative function for a Gaussian. And in fact, if you have just this bound for every t, you just use Markov inequality. Maybe if you want more details, you will get the Gaussian concentration, okay? This is a standard tool to prove concentration and behavior of the tails. You just look at the exponential and you try to work out some bound. Now, if we pick as our sigma, which must be a product, we pick a multiple of the identity, so identity divided by 2 to the n, so that the trace is 1. But this is actually what is called also a maximally mixed state. But anyway, it's a product state of the identities. The tensor product of the identities is identity. So we only use it in that case. Because now, if you plug the identity, you see t times the trace of h rho, start from this quantity here. Actually, since we are assuming that the trace of h is 0, means the trace of h sigma is 0, because sigma is the identity. So you can get for free at least now the difference between rho and sigma. Now, t times the trace of h, and now we have the discrepancy, right, because you have rho minus sigma here. But now h has a Lipschitz norm smaller than 1, so you can always bound from above with the maximum over all the possible 1 Lipschitz observables h. And the maximum is precisely the Wasserstein 1 distance. And we have also this factor t that we never used so far. But what is now the point? The point is you use the transport entropy inequality, so you have t times the square root of relative entropy, okay? Well, and finally you just use, how do you call it? AB is smaller than a squared plus b squared over 2, essentially, okay? Maybe we just need to specify a bit who are a and b, but Young inequality, maybe Oliver will, as you already used it yesterday, right, this simple argument here. So you have this, and so finally you know that you have at least this inequality. This is still not what we want, but we have some expectation, quantum expectation of h, and we have a relative entropy. But we see already at t and t squared, this is good. Because now what you take, okay, you take a special case of rho. You take the so-called the Gibbs state, right, given your h. So you take e to the th and you normalize so that it is a state. Now in that specific case, you can actually show, of course, that the log of rho is th and some normalizing constant. So that if you plug in this case with this choice, you see you have that the relative entropy becomes the trace of h rho, okay, minus log trace of e to the th plus another factor, okay. So, but now the point is that you can really compute explicitly this, and this will cancel out the left-hand side. So you are left really with an inequality that you want up to taking an exponential, okay. So actually, if you think what you need, you don't even need all the possible rows, right? You need to explain, to find this transport entropy, but also for rho, which are Gibbs state with respect to your observable. Okay, yeah.
Where does the t squared enter on that equation on part 2? Because like everything else there does not depend on t. So this in the last inequality here, like rho and sigma.
Yeah, maybe here I'm missing. I did something wrong here. You have a divided by t, maybe. I did something wrong here, right? Right, I did something wrong here. Okay. Now, if you plug, you see you have log of t. Yeah, let me see. So you have t. Where I'm wrong here now. So, so if you plug this state here, the log will be th. So this will give you a th.
You're just applying the formula for the relative entropy.
Yes.
Phase rho ln rho minus the other one.
Yes, I agree with you, but I don't see now anymore the t squared.
No, you move the t squared into the square root, and then you use your ab is less than a squared b squared by splitting n times t squared over 2 and s rho sigma. Then you have your inequality there.
Right, so you're right, because you move it inside. Yes,
inside,
sorry,
yeah,
I was thinking about yes. So you're not using, yes, if you want, you're using it if you want.
No, and then you have another factor tb because it comes from the.
Yeah, but this simplifies. You see, we have autos on this side, so this simplifies. Okay. No. I mean, this is. I mean, it's written now in a quantum setting if you want, but you're just using. This is a very standard argument. What I'm not very sure, Marius maybe can comment on this, is whether you can always also go in the opposite direction. Because now, if you do a similar thing with a state which is not the identity, what we're able to show is not.
We claim that these inequalities, Talagon inequalities in concentration are equivalent, but it's a hard proof, and I will talk about this in week 2.
Right. Okay. So. If you're interested in this subject, we have people who are more expert than me. But what I can tell you is that if you plug a state which is not a product, at least what happens on the left-hand side there in 1 is that you end up with a quantity like this. Not the it's a usual issue with the exponential of the sum of matrices. In the classical case, you have the exponential of a plus log of b, and this is equal. But in general, you would have only an inequality which goes in the wrong direction there. So what you can prove if you have a general sigma, because here we only use the sigma of this kind. But we know that the transport entropy holds for a general sigma, but you end up with this on the left-hand side. So I don't know if this can be of any use.
This can be very, very delicate.
Yeah, no, it's... Okay, let me just conclude with other applications of this kind of Wasserstein 1 distance. So there's been some approach, some more, okay, it's not really using exactly this distance. So they try to relax a bit this notion of Lipschitz semi-norm. You look for operators in a given class. You try to control the Lipschitz semi-norm. And then you use this distance that you find as a discriminator in this setting of Wasserstein generative adversarial networks with a Q because they become quantum. Now, if you're interested in this, it mixes a lot of different, say, ideas and maybe interesting, but I would say it's, don't ask me too much because I think they're out of my range for the moment. Another interesting point is this idea of quantum Ricci curvature that can be extended to many settings, not only of this Wasserstein 1, but was explored by Gao and Cambyse-Rouzet recently. Now, but if I should mention what are the main problems related to this and other approaches. So the first is an efficient way to compute or approximate this Wasserstein 1, because when you plug it here, again, they do some relaxation and stuff, but it would be interesting, for example, to have a good algorithm for the actual Wasserstein 1 distance, maybe. And then other problems which may be interesting is, okay, there's an entire zoo of geometric inequalities on the quantum Hamming cube. These two inequalities that I showed you are just maybe the most famous ones, but we could explore other kind of inequalities with this, related with this distance. And again, related to this curvature notion, if we can find in terms of this distance good estimates for mixing times for semigroups. Okay, I stop here. I hope you have enough of me, so I'll accept questions, but we can really stop for the moment. Okay, thanks a lot.